Okay, so good morning. And so last lecture, we did work out what the orthogonal group. So we worked out what this group was, O13, and we saw that this as a set is a disjoint union of four things. Okay, so and we also saw that SO13 is the plus, is the orthogonal, is the Lie group. O3 of course is not, O13 is not, but this is a Lie group. So these are simple facts. Okay, and so we want, so in physics we want objects that transform nicely under SO13 plus. Okay, and so we'll see how to construct them. Okay. So I'm ignoring P and T transformation. So these are things which you put on top of each other. Okay, so we already know one only. Okay, we already know about one set of objects which are four vectors. Okay, so notations will either be V bar like an underscore, or if you want to give an index, we write mu, and mu runs from 0, 1, 2, and 3. So Greek indices go this way. So this is our notation. And we know that we can write like this: V prime equal to under where lambda belongs to SO13. Okay, if you want to put the indices, we'll put it like this: V prime mu equal to lambda mu, of course, repeated index, so Einstein summation assumed. Okay. So how do we construct other objects? And we will use the tensor method. People get scared when one uses the word tensor. It is just pretty trivial. You will see tensor method to construct. Okay. Other objects. I'm using objects, but actually the correct word is other representations. I'm calling them objects which transform nicely. Okay. So we had already seen this. We call under tensors of SO3. Okay, so we had done something like this. We said T prime I1 to IR, tensor of rank R. This transforms like R I1 J1, R I2 J2, R IR JR, T J1 J2 JR. Okay, so this is how we define tensors. Okay, so this is a rank R tensor. Okay, similarly, okay, we define tensors SO13 plus by a similar formula. Okay. One more point to make here, which is distinct, is that Einstein summation is assumed, but the modification in the Einstein summation is that you should always be summing one lower index and one upper index. We'll explain what a lower index is and what an upper index is. Okay. So we only have defined objects which are like this with an upper index. Soon we will define something which has a lower index. They will be almost the same, but they'll differ by signs. And you can ask, why didn't we see upper index and lower index in SO3? The reason is upper and down. I think they don't make any difference. But here it will make a difference, as we will see later. Okay. So is this definition clear? So this is the definition. This is okay. So R equal to 1. If R equal to 1, we get a 4 vector. I'll give it another name so that we call it a contravariant vector. The correct thing is to say it's a contravariant vector of SO13 plus. But in the context, we'll just use the word vector and or just say vector. But you have to tell me which, if it's vector under SO3 rotations or vector under SO13 plus. They are not the same, as you know. Okay, so R equal to 1 we know. But if we take R equal to 2, we'll get an object like this. But like before, we can write it as a symmetric, antisymmetric. There will be 2 types. And actually, you can break this up into, we have to discuss what is trace, we'll do that later. Okay, so R equal to 2, these are second rank tensor. These are 2 possibilities, and so you can, if you remember the same arguments we had in rotations, which says that if a tensor is symmetric is symmetric once under rotations, it will continue to be symmetric. Same thing happens here. And again, covariance of this thing says that if any tensor which vanishes in one frame will vanish in all other frames. That means if T nu1 nu r is 0, then it will be 0 in all other frames. So you can convert this statement of symmetric, antisymmetric into such statements about a tensor vanishing in some frame. It will vanish always. So the property of symmetric is or antisymmetric is an invariant under Lorentz transformations. Okay, so I'll give some example now. So it turns out a very important example of this thing. So electric and magnetic fields electric and magnetic fields combine form a second rank antisymmetric tensor. You can go back and check. Antisymmetric means mu takes 4 values, mu also takes 4 values. Antisymmetry will tell you 4 into 3 by 2, 6. So you can see that it has 6 antisymmetric second rank tensor under SO13 has 6 components. E is 3 and B is 3, so the numbers work out. But we can be much more this thing, so we'll just call it, the notation here is F mu. This is definition. Where Okay, so there is a minus sign here, okay, in the upper d nu and exercise. Okay, so this is so I've defined all these things. This is just a derivative. It's a four derivative as opposed to a three derivative like that. So, but it's natural generalization of del. It combines the spatial time derivatives with the time. Spatial derivatives with the time derivatives. So this is what happens. Okay, so you can exercise, verify that f0i is proportional to here. It might be equal to, it's plus or minus, that's all. Okay, check that. And fij is proportional to epsilon ijk dk. Okay, so you can see that we saw under Lorentz transformation, A formed a 4-vector and it's a components mix, and we also saw E and B mix, and this is what we get. Okay, now this is one thing. So in particular, once we have this, we can work out the transformations of the electric and magnetic field under finite boosts. Why is that? Can someone tell me how I would do that? This is it. So you have to just write it out in components, and you should see what you get. Okay, this is the formula. Okay, so I express this. B prime as well, and of course, and U. Okay, so you can go back and check. We know it to first order, but we actually can write it to all orders. Maybe I can write it out for you for completeness. So let's do that. Okay, so which I'll write out for you. It's very simple. It's kind of nice. It is E parallel prime. So E parallel is the component which is parallel to U. E parallel prime is equal to E parallel. The other one is E perpendicular, which is a vector now. Prime is equal to gamma times E perp. Okay, so you can see if we set gamma equal to gamma, remember what gamma and beta are? Okay, gamma, so beta was, gamma is just So gamma is something which is strictly greater than or equal to 1. Okay. So you can see that the U-square corrections all nicely combine and come here in this form. And that is, the parallel guy does not see any corrections. Okay. This is something which you should be able to check. Okay. Is this clear what I've written? But it's an exercise for you to do. It's worth doing at least once in your life. Okay. So are there any questions and comments? Okay. So I'm going to define for you another set of things we call covariant vectors. Okay. These also transform. Okay. So let's say, V mu is a 4 vector. Okay. Starting from that, I'll construct, define V lower mu, this is definition, is to lower eta mu nu V nu. Okay, this is definition of this. So we call this fellow is called covariant. Okay, and another point here is so we can also let's leave it at this. So let's work out what V0 will be. V0 will be eta 0 nu V nu, but only eta 0 0, which is plus 1. So this is just V0. Okay, but what about Vi? Remember, I runs from 1, 2, and 3. It runs only over spatial indices, and this is equal to definition eta I nu V nu. So we know that eta I is minus 1 spatial thing. So this is minus Vi. Okay, so if V mu is equal to V0 and a vector, okay, then again V lower mu, it's better to think of it as a vector. Okay, this is convention, this is column vector. Okay, in particular, if V and W are two contravariant or 4 vectors, okay, then their inner product or dot product is the Minkowski product. Okay, so it is which we can write also as follows. Okay, so you will see that if W equal to V, we got what we wrote. We got that funny norm. Okay, so that gives you this thing. Okay, so and you can check that this is equivalent to writing that. Okay, so this is what we get. But now you see something interesting here. This is the combination. Sorry, I made a mistake. This is upper index. So you can see this is W. So, and if you want to write it properly, we want to write it like this. We want to write it as W mu V mu. Or we can write it as V mu W. Okay, the reason I'm writing it in this order is because this we are thinking of row vector. So this is column vector. You put them together, you get it. Okay, so this is a Lorentz scalar. So this is the analog of dot product which we have for rotations. Okay. So I want to work out one example. So d mu. Yeah, go ahead.
How do we decide for eta which indices to place where, like among?
Eta is symmetric, it doesn't matter. Eta, okay, so there are two etas, one which is, eta is either both lower or both upper. Okay, so yeah, let me write that. Good point. Okay, so you can do this. Eta mu nu, eta nu rho. Okay, so this is summed over this nu by, this is delta. Okay, so this is Kronecker delta. Okay, so this says that these are inverse matrices, but as matrices they're identical because it's diagonal matrix with ones and minus ones. Okay, so this is okay. So this is so eta will have these two things, two possibilities. Okay, so yeah, I want to say one more property. You can check that eta prime mu nu is equal to eta mu nu. That is, it is isotropic, or rather invariant under so in all frames it looks the same. Okay, good. So let's look at d mu. If you work, so this should be d upper nu. Sorry, d upper nu. Okay, so this is a definition. But if you work it out, you will get this will be d0 and del plus del. Okay, so d mu, this has no minus sign, is, if you want, I'll use the word naturally. Someday you will understand what I mean. It's naturally a covariant 4 vector. By that I mean the spatial and time derivatives combine, they combine naturally to form a covariant 4 vector. Okay, so this is very, very important. So now we can write Maxwell's equations. I can write in a covariant form. Okay, so I write this. Okay, where J nu up to factors of psi is just phi and J vector. Sorry, not phi, but rho. Okay, I forget it. It's probably 0 or something like that. Okay, you can check that. So this is this gives us this gives 4 of the Maxwell's equations, but then we need so this gives so this is equivalent to okay, so this is in Gaussian units. Okay. but we still have four more equations to get. And so there's a trivial identity, which is a little bit more complicated to write. I'll write it and then we'll discuss. So cyclic permutations I'm doing out here. Okay, so this is identity which appears in different contexts. It's a trivial identity in some ways. What it says is that if f mu nu is as we define, d mu a nu minus d nu a mu, then it just says that if you put in those values, you'll see that like in the Jacobi identity, sometimes we just check that pairs cancel. That's what happens here. But this is actually the same as del dot B equal to 0 and del cross E minus 1 by C d. This is all in Gaussian units. Okay, we wrote those. So you can verify this. You can check this. But what is very important is that you look at these equations. So you can see that left hand side is a 4 vector because mu nu mu are summed over, so that's cancelled in some sense. So left hand side is a 4 vector, right hand side is a 4 vector under SO13 plus. So you see that this equation is totally manifestly symmetric, manifestly invariant under Lorentz transformation. Similarly, this looks like some rank 3 tensor. Okay, and it says this combination is 0 in one frame, it will remain 0 in all frames. So what we have achieved here is covariance or under SO13 plus is manifest. Okay, manifest means visible. There's nothing to check. All I have to tell you is f mu nu is a second rank antisymmetric tensor. Okay. One more equation that we know, equation of continuity. It's just, again, you can check this. All these checks will take you just like, probably total time of 10 minutes or so. Okay. So I'll pause here so that you can ask questions.
So just one question. I was asking that you defined those tensors at the time you defined tensors, you used the word nice transformations. Can you say some more formal terminology for that?
Nice
transformation. What makes nice transformations nice?
This is what is nice. So it says that if one tensor vanishes one nice property which is very important in all these things is that if a tensor vanishes in one frame, it vanishes in all other frames. It's linear. It's a linear transformation like this.
So can we use the words like isomorphism?
It's not isomorphism. Isomorphism is two things being equal. No. Okay, that's not what this is saying. What this is saying is that if you give me objects like this, so in particular, if you write equations involving tensors of SO13 plus, those equations will remain their form will not change in any other frame under Lorentz transformation. You just go ahead, replace everything by primes, you're done.
Yeah, so the form preservation is the definition of homeomorphism.
No. I'm sorry. You're misusing some terminology. So I know what you're saying, but no, I don't want to use that. Okay.
Okay, sir.
Okay. So this is the key. Okay. The correct word is these are irreducible representations of SO13 plus. What is that? Okay, so I mean, this sort of is a nice completion of our prelude. We started out, we saw how first order transformations lead to some suggest how things should mix, and then we use the fact that we look for a Lie group which will give that under infinitesimal things, and that kind of fixed the finite case. And now we are able to actually see that things are here. I mean, this is like the culmination of all these things, these two equations. Actually, this and this equation, all three equation of continuity, all of them are nice. So you can see this is a scalar under. Okay, so there are no free indices. One, and if you see, I'm careful, one lower, one upper, everything comes. Okay, so that's what that's all I want to say. And so this sort of concludes one part of the story, but I just want to discuss some implications of Lorentz boosts. Okay, in physics. Okay, so there are two nice consequences for predictions that follow. Okay, I want to discuss this. Okay, so actually three, but okay. So the first point is that so we saw that space and time mixed okay, and this is kind of counterintuitive because if you go back to Galilean thing where our intuition comes, we know that we can go ahead and synchronize our watches with some other guy, and we hope that our watches will remain the same in future, right? If you adjust it and we have matched them, what we will see is that that's not true. Okay, so Lorentz boost messes up those things, and because there is mixing of space and time, and in particular, okay, so that is something. Okay, so dynamics or motion in SR happens in not space and time, but in space-time. You form a single word, okay, which is Minkowski space. Okay. So Minkowski space means, okay, so we have coordinates which we will write as x0, which is CT, and x, which is the usual vector. Okay, so this is what we will do, and it forces us to treat space and time on par. Okay, so we'll define an event is a point in space-time in this setup. Okay, and so if you have two events, A and B, okay, we view them okay, so I have to tell you the coordinates of A, space-time coordinates of A, space-time coordinates of B, and then we can define a separation or a displacement. So delta infinitesimal, guys. So delta x, this will be an infinitesimal displacement. Okay, so this is a 4 vector, and what one does is one defines the length of this 4 vector, which is okay, so this is Lorentz invariant. Okay, so so now I'll draw a picture. I can't draw in 4 dimensions, so I'll draw a simple picture, which we will try to understand. And just give me a time. I'm trying to figure out what colors to use. Okay. Okay. So let's just focus on one direction, X. Okay. And we'll choose the other axis to be CT. So I'm looking at only one space and one time dimension. And so we'll start, we can ask, for instance, let's go back to this, where is delta S? Here. Okay, suppose, so what is delta X0? It is just C delta T. Okay. So we can ask how a light ray would. So let's say that we start with the origin and we ask what happens to a light ray. And you will see in this thing that it has to move at 45 degrees. Why is that? Because for a light ray, its speed is, so for a light ray, speed is C. So you will see that this, this is equal to okay, where I'm just saying U is just delta X by delta T. Okay, so you see that if U is C, magnitude of U is C, this becomes 0. So what you will see here is that this means it moves at angle 45 degrees. So let's do that. Let's pick a different color, draw light rays, and draw straight lines. Trying to move it. It's not moving. Why? I give up. This is even worse. Oh, I think I'm doing something stupid. Okay, I stop here. Okay, so let's just assume that these angles are 45 degrees. Okay, so if I have a light ray coming from this side, okay, so so now there are so this is just so this is how light rays this thing, and you can see that for light rays the delta S is 0. Okay, And one more thing we see here is delta S square could be any sign. It could be positive, 0, it could be negative. Okay, at least we see that for light rays it is 0. We can ask what is it for a particle. Suppose a particle is just staying at some point. It will remain at this thing, so delta x will be 0. So for a real particle, we will see that delta S square is always greater than 0. Okay, so let me mark some regions. These are regions. This is one region. Let me change color. Okay, so okay. So let's look at this. So I will mark some things now. Go back to white. So this region is so any point in this region, and even here this region is also delta S square greater than 0. Okay, so these have names. So what we see here, with respect to this point origin, this term, all points here are in the past. So this is called the past light cone. You'll see why it's called a cone. And what should we call? So these all points that are here will be in the future light cone. Let's call this point O. Okay, so let's for a moment assume that there is a point in the future light cone of O, and also let's assume that that we cannot do anything faster than the speed of light. Okay, so what it means is that a person in O can affect all points which are only within the light cone, future light cone. That's one point. And you can ask, what are all the points which could have affected O? You have to look at all points. So if you take a point here, to come from here to O, you need not go at a speed of light. You can go slower than the speed of light. But if you have to go from here to here, you have to go at a speed faster than light. So that's not. So these are not accessible. So these regions are not accessible to the point at O, or the event O. So they will not be affected by those things. That is one thing. There's another observation. So if you give me a point which is here in the light cone, there exists a Lorentz frame where you can map it to here. Okay. Similarly, if you give me a point here, I can always find a Lorentz transformation where it will get mapped to just have delta t being 0. Okay. So this is something which you can get some trivial algebra, but this is a very important picture which emerges. Okay. But this picture is in space time. Okay. So there are terms, so delta S square greater than 0, delta S square equal to 0, and delta S square less than 0. These are names. So this guy is called time-like. This is called space-like separation. What should we call delta S square equal to 0? Light-like. Only light can go. Or anything which goes at the speed of light. Okay, so these are the few things. Okay, so pick a point. So with respect to O, okay, if you light rays in all directions, if you send out light rays in all directions, form a cone. Okay, that's why it's called a light cone. So let's do that. So we have a point O. So we know things follow 45 degrees. So it goes like this. But now there are other directions, so the cross section. Okay. So in 3 dimensions, so this cross section will be S2 sphere. Okay, and so this is this is a surface. So this is a surface of a. So that's why it's called a light cone. In 2 dimensions, you can see it's just a surface of revolution. Cross section is a circle, but it is something. It's a sphere in higher dimensions. Okay, just that's just a picture. That's why it's called light cone. Okay, so I think I'm done here. And before we proceed, so next what we want to do is we have to do mechanics in SR. Okay. There is another thing which I should have done today. I got distracted, but these go by the terms like Lorentz contractions. And time dilations. I will give you notes on that. These are simple things. Okay, I will share notes. Okay, so for this, I will put out 2 videos, but otherwise I will give my lecture tomorrow. Okay, if I cannot. Okay, so we will see that how to handle acceleration. So here we will just see what is F equal to ma equals to what. Okay, so we will see that we will write something like this: F equal to ma mu, but we need to define what this F and what is a 4 vector, which is a force, what is a this thing, and these turn out to be not so nice 4 vectors. There are some constraints they have to satisfy, but we can handle accelerations in SR, etc. Okay, particles can accelerate in SR. It's not as if just as they could accelerate even in Newtonian mechanics. The same thing happens. Okay, so I'll stop here and pause for questions.
Why delta square greater than 0 is called a future cone? You refer to
No,
the
it's not. It's not just that. No. It's delta S square greater than 0 and sine of delta t. That's the Lorentz invariant, which is greater.
But the delta square less than 0, that portion I was asking.
Why is it called? Space-like. It's called space-like.
Means that region cannot be accessed at all. So
yeah, no, it's like this, right? Consider 2 points which are separated in your frame. They're at rest. They're say 1 centimeter apart. Okay, at the same time. But if you want to, you cannot access that point immediately because you'll require, let's say the separation is some x, then you'll require, at least if you send something at the speed of light, you'll require some time x by t. Okay, I'll draw a picture, I think that will help. Okay, suppose we have 2 points at the same, okay, A and B. So if I send a light cone, a light ray, it will move at 45 degrees and it will come to this point only at a later time. This is B prime. So remember B is a point in space size. B cannot be accessed by A ever. B prime can, of course, because it's a point in time. That's why there are 2 points which are at the same time. They are in different spatial points. So it's a space-like separation. This is the same time, t equal to some constant. If you send a light ray or something, it will move forward in time. You can reach the spatial point B, but only at a later time. So any 2 points which are spatially separated in your frame are space-like separated. Delta x is non-zero, but delta t is 0. So delta s has to be negative. Is that clear?
yes.
Okay. Any other questions?